Hello everyone, welcome to my talk. My name is Xuanqi from Xi'an University, and I'm here to present FairNeuron, a deep neural network model automatic repairing tool. This work was done in collaboration with Zhai and Shiqing from Rutgers University, Chao and Yufei Chen from Xi'an University, and Qian Wang from Wuhan University. Recent advances in deep learning have made it possible to benefit users in many fields: machine translation, autonomous driving, virtual assistant, disease diagnosis. These convenient tools are inseparable from deep learning. One of the most trendy applications is decision-making systems, which requires a high utility DNN with fairness. However, people have revealed many fairness problems in AI systems. The Google Photos application uses an automatic tagging tool to help organize uploaded images and make searching easier. But the AI software mistakenly described African-American computer programmer Jackie Elson and his friend. Some people commented it the first instance of AI racism. Maybe some people think it's just a little mistake that doesn't matter. Then what about the fact that AI may influence judges' decisions? Compass is a case management and decision support tool developed and owned by Equivent, used by US courts to assess the likelihood of defendant becoming a recidivant. Compass has been used by the US states of New York, Wisconsin, California, Florida, and other jurisdictions. Overall, Compass correctly predicts recidivism 60% of the time. But the ProPublica investigation team found that blacks are almost twice as likely as whites to be labeled a higher risk, but not actually reoffend. It makes the opposite mistake among whites. They are much more likely than blacks to be labeled lower risk but go on to commit other crimes. Existing work has proposed methods to improve DNA fairness by removing such bias. Fair adversarial discriminative is a fair adversary framework, which leverages gradient reversal to fix model fairness problem. The authors introduced a predictor network to maximize accuracy, and the adversary network tries to maximize fairness in protected attributes. Ethical adversaries is another framework. It has two parties. The feeder plays the role of an external adversary, and the reader represents the protected attribute. It is an iterative adversary training procedure. However, they have some limitations. Firstly, they introduce another model as the adversary in training procedure. Inheriting from existing adversarial networks, training such models is not easy. Secondly, there is no guarantee that training such adversary network will always coverage for now. Besides, this model structure is more heavyweight and less efficient. We managed to overcome this limitation. But before I introduce our algorithm, I want to briefly introduce why bias happens in a DNA training, which is helpful to understanding our idea. Let's consider a simple fully connected model. To optimize model's accuracy, we need to maximize model's ability to predict the label, just like a typical neural network structure. To optimize fairness, we need to minimize the confidence of the model to protect attributes. When we try to fit both objectives into a same loss function, the problem arises. Existing work has shown that optimized accuracy and different fairness objectives can be contradictory to each other, but not always. Let's consider a benign sample to be fed into the neural network. We show its backpropagation process and use arrows to indicate the optimization direction of the network. The red arrows means optimizer will increase the weight, and the green is the upside. For benign sample, optimizing accuracy target and fairness target will not conflict seriously. If we feed a biased sample, then the neuron's accuracy and fairness optimization will have different direction. So you see they get conflict with each other. Now, based on this observation, we can propose our idea. We argue that it is not necessary to introduce an adversary that detects the potential conflicts of optimizing the accuracy and fairness. In order to achieve the above goal, we design FairNeuron, which consists of three modules. The whole system In order to achieve the above goal, we design FairNeuron, which consists of three modules. The whole system starts by taking a biased model and its training data as inputs. Firstly, FairNeuron performs neural network slicing, which detects neurons and paths that have contradictory optimization directions. Next, we leverage such paths to identify the samples that cause such effects, known as the sample clustering. By doing so, we can separate the samples into two clusters, biased sample and benign samples. Lastly, we perform selective retraining to enforce the model to learn unbiased features. Then let us dive into how each step works. Instead, we detect and solve these conflicts at neural level. In order to achieve the above goal, we design FairNeuron, which consists of three modules. The whole system starts by taking a biased model and its training data as inputs. Firstly, FairNeuron performs neural network slicing, which detects neurons and paths that have contradictory optimization directions. Next, we leverage such paths to identify the samples that cause such effects, known as the sample clustering. By doing so, we can separate the samples into two clusters, biased data samples and benign data samples. Lastly, we perform selective retraining to enforce the model to learn unbiased features. And let us dive into how each step works. We will use the same simple example to demonstrate how neural network slicing works. First, we perform path profiling. Specifically, FairNeuron calculates the average activation value of the neuron for a given dataset, and the results are all set to 0 here for simplicity. Then we feed individual samples into the model and calculate its relative activation value on each neuron. Here we assume this sample's activation value are 3, 1 in input layer. By forward propagation, we can get the response of each neuron in network to the sample and record the activation value differences between the average activation and the value for this concrete input, which help us estimate the contributions of each neuron to the output. Finally, we backtrack the contributions of neurons to get the activation path. Starting from the output neuron, we iteratively compute the contributions of the previous neuron, plot them in descending order, and add the key synapses and corresponding neurons into the path set. Here we can see max output value is at N42. Then we compute the contributions of the second last layer. N31 is 0 times 2 equals to 0. N32 is 12 and N33 is minus 3. If we set the threshold gamma at 0.8, then we just pick N32 into path and do not add the others, because 12 is greater than 9 times 0.8. Similarly, we compute the contributions of the second layer and the first layer. Now we can get the path. We use one hot code to represent path. Let us consider a simple case. As this figure shows, suppose our training dataset has 40 samples and obtain 4 different paths, A, B, C, and D. We assume the threshold is 7.5 since the maximum of path sample number is 25 and hyperparameter theta is 30%. Then path C and D will both be classified as biased path, which results in 3 samples activating path C and 2 samples activating path D being grouped in biased samples. Finally, we perform selective training on split datasets we got before. We use dropout technique, which enhances model generalization by randomly masking neurons in a network. In step 1, we perform ordinary training on ordinary samples, just like naive model. As we can see, ordinary training means deactivating the dropout layers for training. In step 2, we active dropout of neural network and feed neural network with biased samples. By doing so, we enforce these biased neurons to learn more unbiased features rather than biased ones, mitigate the fairness problem. So we don't need to change the model's structure, just need to change the activation state of the dropout layers. To evaluate our system, we aim to answer 4 research questions shown on this slide. We performed our experiments on 3 popular datasets, and in total, we collect 4 popular fairness fixing algorithms as baseline and compare them with FairNeuron in terms of both accuracy and fairness. Let's briefly review the fairness metrics before we present our evaluation results. We choose 3 most common notations, DP, DPR, and EO in our study. DP views fairness as different subpopulations should have an equal probability of being classified to the positive label. DPR is similar to DP. The key difference is that it represents the equality or similarity of prediction on different groups as a ratio instead of a substitution. A limitation of DP and DPR is that they do not consider potential differences in compared subgroups. EO definition overcomes this problem by conditional independence. RQ1 is to evaluate how effective is our system fixing bias model. The average accuracy of FairNeuron is the highest among all models with fairness constraints, and even surpasses the naive model on German credit and campus dataset. Compared with the other algorithms, FairNeuron achieves the best fairness performance on census and campus. However, the EO and DP results of FairNeuron on credit is not satisfactory. After our analysis, we found that our neural network slicing is not fully functional because credit only has 600 instances. So how to improve the utility of models training on such small dataset will be one of our future works. Then in RQ2, we evaluate efficiency of FairNeuron. This figure reports the efficiency of naive model, ethical adversaries, and FairNeuron. We normalize the efficiency of naive model to 1. For naive training, the runtime overhead all comes from the training procedure. But for FairNeuron, the hyperparameters tuning takes a large ratio of total time usage. The FairNeuron takes only twice of the time usage of naive training on large dataset like census. But on small dataset like German credit dataset, it takes a relatively a long time. Overall, FairNeuron is more efficient than ethical adversaries in fixed models. with an average speed up of 180%. RQ3 is to explain how we choose the configurable parameter in our system. Gamma represents the threshold of neuron activation, and its value affects the complexity of the path. As its value decreases, more neuron and synapses are included in the path, resulting in a more complex path. Theta represents the threshold of neural network slicing. The lower is the theta, the fewer paths are classified as abnormal. We use open source retune tool to perform grid search on a small subset. We use open source retune tool to perform grid search on a small subset, which drawn from the training set in a certain proportion. All the details have been shown in our paper. The last RQ is to explore the possibility. The last RQ is to explore the possibility of FairNeuron in fixing vision models. For image dataset, we use class-wise variance and maximum class-wise discrepancy as fairness metrics. We leverage a 4-layer fully connected neural network trained on MNIST and the ResNet 18 trained on CEPA10. We compare FairNeuron with a naive model and random dropout. As we can see, FairNeuron improved the model fairness by 20% for MCD and 80% for CV. In conclusion, we summarize and formalize definition for fairness bugs and reasons in training procedure. We propose FairNeuron, a lightweight algorithm to effectively fixing fairness problems for deep learning through path analysis. Our algorithm combines the path analysis procedure and the dropout procedure to systematically improve model performance. FairNeuron searches bias instance with the guidance of path analysis and mitigates fairness problem by dropout training. Our evaluation results show that FairNeuron has significantly better performance both in terms of effectively and efficiently in fixing bias model. For the CNN model, we can only perform FairNeuron on the last fully connected layer, so its performance is not ideal. We will improve FairNeuron on CNN in the future. So much for my presentation. Thank you for watching.